name is Charles and I'm going to be taking from terms of slide 1 to slide 8 via dealing the contact in the political fabrication. And when we go to the next slide, we have the abstract. This is just giving an overview of the project that we're working on. And under political cloud is a verified cloud that poses significant also money worldwide. And in traditional fraud detection models, uh, this one is a tool and large data sets, which could increase the fraud cases. So, when you have the detection whereby means it can have large data sets, this it enables it to learn the patterns used. Then hybrid quantum classical approach. This is the combination of classical computers and quantum computers who leverage the strength of both algorithms. Then focus on computational efficiency and the accuracy. Then they have in the keywords, under the keywords, you have quantum machine learning. And quantum machine learning is this a field. Um, it's just a field for the application of quantum computing, so machine learning projects or tasks. Then quantum computing is a field of computing that uses the principles of quantum mechanics to process information more efficiently than the classical computers. And we have included fraud detection and detection, the process of identifying unauthorized transactions that take place within the card and the credit card, the banking system. Then we have in anomaly detections. The technique is to identify unusual patterns that do not conform to the expected behaviors of the system or the fraud detection. Then we have in the qubits. Qubits, these are the fundamental items or fundamental units of quantum computers that are used to perform calculations and they are faster than classical bits. That's what I can say about qubits. Then we have in the introduction and the objective that we have to explore how quantum machine learning can improve fraud detection. Then the context, financial fraud, credit card fraud, causes billions of users in annually. Then the problem that we have, traditional models struggle with evolving fraud patterns and high false positive rates. This is true because traditional models cannot handle large data sets. Yes, people can come with different credit cards if they can access the people's money. Then we have the problem statement and the credit card fraud detection faces challenges that we have in analysis and the evolving fraud strategies. Fraud stars continuously adapt new changes or new methods or new patterns, making rule-based fraud detection ineffective over time. Then difficulty in adapting new fraud patterns, traditional machine models require frequently training. You need to train these devices with more data sets in that they can learn more quickly, which can be inefficient as long as we give it a lot of data sets, then it can be inefficient. Then we are having high false positives. When legitimate transactions get flagged as fraud, leading to inconvenience for the customers and financial losses for businesses as people lose a lot of money. Then need for quantum machine learning, the good result that can adapt in real time to know fraud techniques, then can handle large data sets, then can reduce false positives while improving fraud detection. Then when we go to the next slide, we have the technical challenges and we have in hardware limitation. Quantum computers are still in their early stages. They have just introduced them. They have limited qubits and processing power is still low. The ARX are due to high hardware instabilities. Then you have noise and error correlation. Noise and error correlation, this can cause the system to change its accuracy or change its performance algorithm result. They are sensitive to environmental noise, leading to calculation errors. Then we have in algorithm development. Algorithm development is very inefficient quantum algorithm. The fraud detection is a complex. The quantum machine learning algorithms are still being researched and they require optimization. Then adapting classical machine learning models for quantum computing is also so complex. Then when we go to the next slide, We have the data preparation. When you take a lot of time performing EDA, data cleaning, removing missing values, this is a bit time consuming. Uh, we have where classical data must be converted to quantum compatible formats, which is time consuming also. Then you have in scalability and interpretation. Quantum models are difficult to understand why a transaction is flagged as a fraud. Yeah, and these systems are not yet scalable to handle large data sets because of the memory storage. As I told you, they are still in the early stages of developing them. Then we are having the proposed solutions, and we are having the algorithm that are going to be used. And here we have the quantum linearity neighbors. This classifies transactions by comparing them to non-fraudulent transactions, and this works well with detecting fraud patterns based on the historical data. Uh, when, when you go to quantum supported vector machines, these are typically helps to separate fraudulent and non-fraudulent transaction, and these use the term called hyperplanes to identify fraud and non-fraudulent. Yes, and they are more efficient than classical supported vector machines. Then we have quantum neural networks. These quantum neural networks mainly uses deep learning models but operates using quantum principles. You can detect the complex fraud patterns that the classical models cannot do. Then we have quantum principal component analysis, and this reduces large data sets into smaller, more relevant components for faster processing, and it helps in detecting outliers or anomalies more efficiently. I'll invite in my next speaker. Begin from there.
My name is Mutsaka Emerson, and I start from where my colleague has stopped. So for me, I'm starting from data sets, whereby a data set simply means a collection of organized and structured data, typically in a digital format, containing multiple records or entries, such as numbers, text images, and other types of information, as like we have seen. For us, our first data set, we got it from the Hugging Face, which have had the 5 rows and 31 columns, and the features were ranging from V1 to V28, and then it has amount and a class. Those are the rows. Then application of TCL for noise reduction, and then the dimensionality reduction. And also we had a second data set, we got it from Data World. It had the size of 284,807 rows and by 31 columns, and the features were the same. V1 to V28 amount, and then class. So we perform the like when we go to the when we go to the next slide, we have the explanatory data analysis EDA, which it is a crucial step in the data science workflow that involves visually and statistically exploring and summarizing data set to understand the underlying pattern structure and then the relationships. So our objective was to clean and analyze data to prepare for quantum processing as our project states. Then we like steps we remove the irrelevant features that's like noise reduction in our data sets. We handle missing values using like mean, medium, and mode. We visualize these relationships between features using the graphs, histograms, heat maps, and so on. Then our outcome was like easier model training, improved efficiency, and then the faster crowd architecture. So our first visualization was the correlation heat map, which shows relationships between features. As you can see, like we have red and then the blue have green there. Like that is how the relationships are being implemented. So we had another one, which is the box plot. It's like for it was revealing variations and then the potential outliers in our data. Yeah, for both the two data set from the Hugging Face and then the data one. Then the third was we use the histogram bins, those like independent bars, whereby it was showing the distribution of features. Yeah, yes, distribution of features, how like they're being distributed all over our data set. So we had the next one, like analysis estimation. This plot was like visualizing the smooth distribution of features. As you can see there, you can see some like they're having sharp hills. So that's how like the features were being. Some like they are very smooth, others were they like having some curves. So that's how the data was being distributed. So lastly, we had the scatter plot showing the relationship between V1 and the V2, whereby the red represents the proud, then the green the like the yeah, the non-proud. So my last part talk about was using a violin plot. What was the importance of it? One shows the comparison of features of feature distribution is highlighting both spread and density. As you can see here, we drew like for V1 the density, the class, then we drew the V1 showing like it's spread and then the density. So these are the visualizations, and that's my part that I have gone through. And I will stop here. I will welcome my colleague to continue from where I have stopped. Thank you, sir.
My name is Karinji Maria Daffin, and I'm going to be taking you through the visualizations of what we got from the datasets that we had from Hugging Face and from data.world. So the first is a pair plot visualization, which explores relationships between the key features and the class distribution. This plot helps identify correlations, class separability, outliers, as well as trends in the dataset. So this actually helps us know, like it helps us detect what will be necessary in detecting the fraud cases during transactions. Then this is a TNCE, which stands for T-distributed stochastic neighbor embedding, which is used for data visualization and dimensionality reductions in which is depicted. It's particularly useful for visualizing complex nonlinear structures in high dimensional data. So high dimensional data is data that cannot be separated linearly. Yeah. And then the next is class distribution between fraud and non-fraud cases. So this visualizes a balance between fraudulent and non-fraudulent transactions. Next is a correlation heat map, which illustrates relationships between selected features, highlighting which features are not strongly correlated with the fraud. So this helps us know which features we may need for the dataset, because some may not have any sort of correlation while others have a strong correlation. So we shall end up removing those with a weak correlation. And the next is exploring relationships between key features and class distribution. This plot helps identify correlations, class outliers, and trends in the dataset. It's a pairwise graph. It compares between, because for now we're using 4 features, we're using the V1, V2, V3, and the amount. So this compares different pairs. Now it's comparing V1 and V2, V3, and the amount to help us see the outliers and the trends in the specific features. And the next is highlights. This is a box plot, some of the whisker plot, which highlights the distribution and potential outliers in transaction amounts, aiding the identification of unusual transactions. Now, box plot can help us see outliers in that the points that are outside our extreme values, now those will be outliers. So it helps us visualize outliers very well. And the next is correlation of features with target class. So this is a correlation map for, it selects the features and the target variable. So it picks out a few features and maps them with a target variable to help us identify which of these features will actually be will help us in detecting the fraud. Then lastly, we have the amount distribution between fraud and non-fraud. As you can see, the fraud is the one in a pink color, then the non-fraud is the one that's green. So this tells us that actually there is no fraud in this specific the transaction amounts between fraudulent and non-fraudulent cases, highlighting differences in transaction sizes. So thank you very much. My colleague will talk you through the rest of the slides.
My name is Apia Diane from Group 18, and I'm going to continue from colleague has stopped. When we look at this graph, we can see it represents the time distribution of transaction, and it differentiates between fraudulent and non-fraudulent transactions. You can see that the fraudulent transactions are represented by red, and the non-fraudulent are represented by green. You can see here the x-axis. The x-axis represents time, the y-axis represents frequency. So you can see majority of the transactions are non-fraudulent, and they have a high density both at the beginning and the end of this time scale. So fraudulent transactions, however, tend to appear more sporadically or say occasionally and in much lower frequency, showing you that, of course, this fraud transactions do not follow the same pattern as normal transactions. And then when we move on to this next visualization, it is a scatter plot, and it represents the time versus the amount distribution of credit card transactions. We can see that amount is on the y-axis and then the time is on the x-axis. So still following the color identification scheme, with fraud being represented by red and non-fraudulent transactions being represented by green. We can see that most transactions are concentrated on the lower amounts. Most fraudulent transactions are located on the lower amounts, like with fewer cases for high value amounts. And these non-fraudulent transactions occur across all time periods, as you can see on the x-axis. And this you can see also that these fraud transactions tend to cluster closer to the lower amount range, and such patterns sort of suggest that these people who carry out these fraud activities might be making smaller transactions to make their transactions less noticeable, to evade the detection system. Then we move on to our methodologies. Our framework utilizes quantum k-nearest neighbors, quantum support vectors, quantum neural networks, and principal component analysis to enhance credit card fraud detection, and especially its accuracy and its efficiency. And then our data processing involves deploying quantum models or simulators and quantum hardware to integrate quantum classical models for improved performance. Then our evaluation metrics such as precision, recall, and F1 score. F1 score being a performance metric used for evaluating accuracy by balancing precision and recall. So these metrics access the model effectiveness. For component analysis, which aids dimensionality reduction, helping to streamline computations. And then feature selection also eliminates noise, ensuring that relevant transaction patterns are retained. And so this overall methodology optimizes fraud detection by enhancing anomaly recognition and utilizing quantum computing's advantages. Thank you.